Welcome to This Explainer. Today, we're unpacking the incredible, frankly almost magical engineering that keeps one of the world's most famous cities afloat. To help us visualize the complex geology and wood structures hidden underwater, we've brought along a crew of adorable feline engineers in this warm paper-cut style. But don't let the cute cats fool you. The science we're about to explore is incredibly rigorous. We're looking at Venice.
So let's dive right into this absolute impossibility. Think about it. Taking soft, marshy, silty clay, stuff you can barely even stand on, and somehow turning it into a thriving, heavy stone metropolis. I mean, it completely defies logic, right?
To figure out how they did it, our explainer covers 6 quick stages. We'll start with the birth of the city, explore this so-called inverted forest, understand why it hasn't rotted away, uncover a hidden bacterial threat, analyze a real case study of structural decay, and then finally look at the future of these miraculous foundations.
All right, starting with Part 1, Birth of a Floating City, Escaping to the Lagoon.
To really understand these foundations, you have to understand the sheer desperation that drove people into a literal swamp in the first place. You know, they didn't choose this location because it was prime real estate. Not at all. It was a decision made out of pure survival. The Roman Empire was collapsing, the Huns were invading, and these desperate refugees, pictured here as our resourceful paper-cut cats, had absolutely no land and the worst possible surface to build on. They literally had to adapt or perish.
Which brings us to Part 2, the inverted forest, a macro-engineering marvel.
Because they couldn't build on top of the mud, they decided to go through it. They imported millions of tree trunks from forests clear across the sea and drove them straight down into the seabed. Just to give you a sense of the sheer scale here, there are roughly 12,000 timber piles driven into the banks just to support the Rialto Bridge alone. 12,000. Just imagine the physical labor of our little feline workforce out there hammering thousands of tree trunks deep into the earth entirely by hand. We've stylized this geological stratigraphy with our feline engineers and their canine assistants, but make no mistake, the science is exact. By driving these massive piles so incredibly close together, it actually compressed the surrounding mud. It squeezed the water out, kind of like wringing a sponge, making the soft clay hard enough to actually build on.
So, the absolutely crucial point here is this 4-step sequence. First up, they installed wooden sheet pilings to dry out a working area. Second, they hammered the wooden piles into the ground by percussion and laid down a flat layer of planks right on top. Third, they built a sturdy basement layer using waterproof Istrian stone blocks. And finally, they constructed the masonry walls above ground. And here's a really cool detail. They specifically used lime mortar instead of rigid cement because it was flexible enough to handle the slight inevitable shifting of the buildings.
Moving on to Part 3. Why doesn't it rot? The scientific miracle.
Okay, wait a second. Everyone knows that if you put wood in water, it rots. That's just a fact. So why on earth are these original piles still holding up an entire city 1,000 years later? Well, by burying the oak, larch, and pine deep in the lagoon mud, the early Venetians accidentally created an anoxic environment. Because the wood is submerged in this thick, dense mud, it's completely deprived of oxygen. That means the fungi and microorganisms that would normally eat the wood literally suffocate. They can't survive down there. And it actually gets even better. Over time, the wood underwent something called mineralization. This is a natural process where minerals from the surrounding water and mud slowly penetrate the wood over centuries. The piles essentially turn to stone, aided by this protective layer of fine mud wrapping around them. They basically inadvertently engineered a petrified forest. How crazy is that? But of course, nothing is perfect. Part 4, the bacterial threat, a microscale complication.
Just when you think the problem is permanently solved, modern science introduces a slightly terrifying plot twist. For a very long time, the geotechnical community believed these waterlogged piles were indestructible, that they'd last indefinitely. But recent evidence shows anaerobic erosion bacteria, these are microorganisms that actually thrive because there is no oxygen, are slowly eating away at the cell walls of the wood.
If you take a look at the dipping trend lines on this chart, you can see how the residual basal density and compressive strength, which is essentially the wood's ability to hold weight, drops significantly over hundreds of years. The really scary part is that the wood might maintain its outer shape, making it look totally fine, but internally, the bacteria are basically rendering it hollow and fragile.
So let's look at Part 5, analyzing structural decay through the Santa Maria Maggiore case study. To see what this bacterial degradation actually does to a real building, engineers turned to the 16th century church of Santa Maria Maggiore. This place suffers from a massive, terrifying 23-centimeter settlement issue. It's sinking. Researchers used some really complex finite element analysis, basically creating a digital twin of the church's underground structure, just to test exactly how the degrading wood interacts with the soil. Now pay close attention to the depth of those short wooden piles in the table. They're only about 1.5 meters long, meaning they sit entirely in that second layer down, the soft clay silt. The crazy thing is, they never actually reach the stiff, strong Corinto clay layer beneath it.
And this graph right here, this is the smoking gun. It shows the time displacement curves. The computer models prove that while deteriorated wood does cause the building to drop a few centimeters, it does not account for the entire 23-centimeter sink. So yes, the rotting wood is definitely a problem, but surprisingly, it's actually not the main villain here.
Which leads us to our final section, Future of the Foundations, Preserving the Miracle.
So what is the ultimate takeaway for the future of the city? Well, engineers proved a few critical things. Yes, bacterial decay is very real. But Venice's highly heterogeneous soil layers have this time-dependent creeping behavior. Over the centuries, the soft dirt naturally squishes and settles under the massive, crushing weight of a stone city. It turns out this natural viscous creeping of the soil causes far more differential sinking than the wood decay alone.
Today, we are actively fighting the water from above with massive, luridly colored flood barriers called mows. And they're working. Since 2020, these incredible barriers have saved Venice from devastating storm surges 154 times. So for now, we're winning the battle against the tides on the surface. But it leaves us with a massive, provocative question. As we successfully hold back the tides of the Adriatic Sea up above, what engineering marvels will we need to invent next to reinforce the naturally creeping soil and the rotting wooden foundations hidden deep beneath the mud? The inverted forest has held up this magical city for a millennium. Will human ingenuity be able to give it another 1,000 years? That is a fascinating question, and something I highly encourage you to keep exploring.
Knowledge grows through sharing. What are your thoughts on today's topic? Let me know in the comments below. Don't forget to subscribe as we continue to grow together.